Hi, so this is the Physics Unit 1 review. So first off, classical physics, some things to remember is that classical physics consists of things that are not too small. It has to be able to be seen by the naked eye. It involves things that are slow, so anything that is less than 1% light speed and a weak gravitational force. And then there's also very important SI quantities to remember. So we have length, which is meters, mass, which is kilograms, and time, which is in seconds. And then we also want to remember that this is what it means to be precise but not accurate, accurate but not precise, and then this is not precise and not accurate, and then this is precise and accurate. And then that's when we go into uncertainty. Now uncertainty is like variables where we might be uncertain about our measurements due to like factors. Maybe we did something wrong with the measuring. If you were dropping a ball, maybe there's wind that blew the ball, and that could have also affected some of your measurements. So we have two types of uncertainties. We have percent and absolute. And to find percent uncertainty, it is the absolute uncertainty over the measured value. So remember that, and then when you're adding and subtracting, you're going to add the absolute uncertainty, but if you're multiplying or dividing, that's when you have to add the percent uncertainty, and then you could use that percent uncertainty and then apply it to your number to find like what the uncertainty number is, that kind of stuff. And then you also have kinematics. And the main things for kinematics is basically we have position, which goes as a symbol D. We have distance and we have displacement. But distance is just how much you traveled, and displacement talks about how much you traveled in a certain direction. And then we have velocity, which is the rate of change of your position. And velocity also is one of those quantities where direction does matter. We also have acceleration, which is the rate of change in velocity. That is meters per second squared. If velocity is constant and acceleration is 0. And then also make sure you have all of these graphs. So we have a position time graph, and then the slope of that is the average velocity. And then for a velocity versus time graph, the slope of that is equal to the average acceleration, which is change in velocity over change in time, and then the area of this graph is equal to displacement. And then in our acceleration versus time graph, when we find that area, it should equal velocity. So those are a few very important things related to kinematics to remember. And then we also have our kinematics equation. So to find which kinematics equation matches your problem, make sure you look for all the variables you see in your problem, both your knowns and unknowns. So we have 5 kinematics equations, and kinematics equations only apply when it's at a constant acceleration. So that's something to remember. And then our steps to solving a kinematics equation is: number 1, draw a picture. So look at what the problem is telling you, read it, figure out what you have, and then draw a picture of what's going on. Identify what you know, and then identify what you don't know, like what you're trying to find. And then you want to find an equation that matches the problem. So to figure out what you have in the problem, some keywords, if it says anything like from rest it moves that means your initial velocity is 0. If it says it stops like immediately right then and there, then your final velocity is 0. So those are some keywords to keep in mind. So at rest, or it stops like completely, something like that. Yeah, and then you want to plug in your numbers or your units, whatever's easier for you. Mr. Ellman teaches us how to do it with variables, but if you have an easier time doing it with numbers, that should still work. And then you have to check to see if your answer is reasonable. Like, does it make sense? Like, you gotta think about it. Are your signs right? All of that kind of stuff. And then we have dynamics, which is what we just learned. So we have 3 laws of motion. The first one is the law of inertia. And that law says objects in motion stay in motion unless that like another force acts on it for it to like move or change directions. And then we also have objects that stay in rest. Objects that are at rest stay at rest. So an example of inertia. So basically if there's a ball and you like roll it, the ball will keep rolling, but because of the force of friction. Force of friction is whenever something is moving or dragging along an object. Friction kind of like is the resistance to that object moving. So that's why eventually that ball is going to slow down. But then if your object is at rest, so say my AirPods, I put it down, it's not going to move, right? There's no other force. Me moving it right there with my hands, that's the force that's allowing it to move. The second law is F equals ma, or your F net equals ma. So you have your force equals mass times acceleration. You can use this to find gravity. So in the last quiz, there was a problem and you had to find what's your gravitational force. And you can use that equation. So what you would do is your gravitational force is equal to your mass of your object times your gravitational acceleration, which is 9.81, which you could round to 10. So keep that in mind. But overall, it's F net equals ma, and F net equals ma just stands for all of your forces added together equals your mass times your acceleration. And the third law is known as action and reaction, meaning so forces come in pairs. So like what that means is, say you were to like hit the table or hit a wall with your fist, the reason why like that might hurt is because when you like hit something, that force is gonna come back at you with the same magnitude but in the opposite direction. So that's why it hurts when you stub your toe and things like that. Also, you really have to remember and ask yourself when we're doing dynamics problems, what direction is your force going in? So remember, if an object is like hanging, the reason why we did that in our problem for the last quiz is because it cannot have too much, like it's because it's hanging, it's affected by gravity, because it's like, it's suspended in the air, so the only thing that's keeping up is the rope, right? And then, but you also have to remember that the reason why we wouldn't use normal force is because normal force is what stops it from like falling through the ground. And if it's in air, it's not really affected by normal force, but it might be affected by gravity, because if it's gravity is what's holding the weight down, right? When you have a rope and at the end there's a block object, this isn't down. If gravity wasn't affecting it, the rope would be maybe a little more curled and it would be up here. But that wouldn't make sense. It's because when you hold it by a chain or by a rope, it hangs down. So that's something to keep in mind. But if your object stays on like a surface, like how my AirPods are on this surface right now, the gravity and the normal force cancel out. So in most of your problems, you might not be using gravity and normal force. So just some things to think about that are kind of important. Let me see, is there anything else? So acceleration is also directly proportional to net external force, and it is inversely proportional to mass. So what directly proportional means is that when there's two things, right? For example, a mass and force. So like for example, or that kind, or mass and acceleration. That's better. So with so say like you have a tiny rock and then you like throw it, it's like gonna accelerate really fast because it's like a smaller object. But if it was a big rock, which means it would have more mass and it would be heavier, it's not going to be as easy, or it's not going to accelerate as much because of its mass. So that means with smaller mass, more acceleration. With bigger mass, less acceleration. That's basically what inversely proportional means. When one is up, one is down, things like that. You see this kind of seesaw thing going on. But then when it's saying acceleration is directly proportional to net external force, that means when the object is like the same mass, like mass is constant, and you have a bunch of the same objects, like say there's a bunch of 5 kilogram rocks, with more force, there is more acceleration. Now the mass isn't really playing a big role because they're all the same, size. So with more force, like the harder you hit it, it should go farther. Versus if you didn't use as much force and you just went like that, there would be a lot less acceleration. So those are some things to keep in mind. If you have any questions after this, please let me know.